This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Alrighty. This was the money shot at the last lecture when I was giving you, the big sort of big word that these slides, example, turn this on, 3, 2, 1, are, we've got strong, that is stress, stiff, 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 four different examples. There's two that were not given in terms of 3 different kinds of strength, 3 different kinds of stiff. But there is the summary of all 6. Material indices associated with this systematic selection process when our objective is minimum mass for either a stiff or a strong object, and the function of which is either tie, beam or panel, tension, bending. They're the, if you like, the 6 variants. And over the other side we've got the whole, if you like, range of material properties associated with material in general. And this is not a, we're not trying to get an equation with an equal sign. We're getting there, here we've got minimise, so less than or equal to. And what's, historically, one of the little conceptual hurdles that students have to deal with is less than or equal to. Minimise, for example, rho on E corresponds to maximise E on rho, as an example. So we minimise that ratio, we maximise, the inverse of that ratio. It's as simple as that. And all we're dealing with is a variation of exponent from unity to 1/2 to 1/3. And so, again, from the last lecture, the idea of function, we've got a series of function options. And also, there's others, thermal, electrical, that we're not even considering. We're just looking at an introductory snapshot. We have an associated objective. And by the by, it's not real in terms of going to a shop, but there is a minimum cost function within this process as well. Now, those students who eventually get a job and say, gee, we're doing a lot of exotic material selecting here, maybe we should spend the big money on something like Cambridge Engineering Selector, which does give some advice about where to buy expensive stuff. But for now, it's just about recognising cost. What is the major constraint? And there's a few ones there. We've got stiffness or strength is the top 2. There can be others. And then we get to our index from that process. And we're after a minimising of that ratio. And by the way, the material indice or index, often I use the capital M. Some references use different symbols, but I'll try my best to always use capital M. And of course, take 2, minimise that, maximise that. Just to encourage everyone in the room to recognise that it's just a less, one side of a curve or the other side of a curve is where we're looking. I'll be getting onto an example to show what I mean by that in a sec. Now, let's have a look at charts for a second. This is straight out of the Ashby textbook. Up on the screen now, Young's modulus across the y-axis and just a whole heap of materials across the x-axis, subdivided by metals, polymers, ceramics, hybrids. And they're identified. I'm not expecting you to read all this stuff from the back of the class, just to get an idea of, here we have a series of bars of various heights that correspond to the range available for a particular material. So Young's modulus is not a number, even for a material. See if I can find one. Steels, it's pretty narrow. it's about 210 gigapascals or thereabouts. There is variation, but not a lot. You can see they're very thin. But we can look at copper. It's a lot bigger. We look down here to some of these polymers and huge variation in stiffness. But note that we've got very rubbery, very flexible type materials. A log scale, and we're down here. You can imagine we're not going to be able to have anything like the stiffness of the metals that we've shown. And even with this simple chart, we get some insights, in terms of the range of Young's modulus we've got available. Now, rather than just having materials across the x-axis, Ashby and others like Ashby have done a similar thing. Am I being recorded? Is the echo up the back okay? Can you hear? Thank you. That instead of just having Young's modulus and materials, let's, for the sake of it, Mr. Ashby asked a few decades ago, let's put another material property along the x-axis. And we have, as a result of that, I sometimes use, in my own head, I say bubble, but they're really envelopes. Envelopes that give us the bound of, if you like, the family of elastomers that are available. Minimum to maximum density, minimum to maximum stiffness, compared to foams, compared to natural materials, compared to polymers, etc. We get an idea of the overall bound, and we get an idea of intersects, where we've got some composites intersecting with metals and ceramics in that zone up there with those three regions. Envelopes, sorry. Now, this one's a bit more sophisticated. And again, where we're usually in our engineering realm of interest, there's an awful lot of stuff up there. But elastomers, foams, etc. It gives us an idea of what's available and where they sit within the Young's modulus or stiffness, density, which has is a measure of weight, if you like, specific, any kind of measure with a specific notion associated with it. It gives us an idea of how various materials can perform relative to each other. Here's the same thing again in a schematic form with a little bit more information highlighted. I'll go back one. People in the room might have noticed these funny little guidelines, and people up the front would have seen eon rho to a power, eon rho to another power, eon rho without any power. Well, it's being replicated here in an easier to see manner, and this is where there is a little bit of power, a little bit of, this is where the systematic thing gets a bit more fun and available to you as a budding engineer. That those earlier slides I was showing you where the development of a material index or indice was being developed, and we had these various powers. Well, in a log-log chart, you can see it there, you can see it here as well, just in that schematic form, we have a linear relationship. And that linear relationship slope has a relationship to that power of E, but it's still a straight line. Now, the tutorial presentation, I call it Lecture 3, there was 3 repeats earlier in the week, yesterday, that talked about that in great explicit detail. And if anyone missed it and thinks, oh shit, I should have turned up, don't worry, just turn up next week. Because we've still got room B for Bravo 102 booked next week. And just ask Saeed or Farouk or send me an email to do a repeat at a particular session. But the notes are all up on PDF anyway. But what these lines provide us with for, axial tension, bending of a beam or bending of a plate, which is, the limit of what I'm worried about for right now, the potential to have a limiting line. That is, we can have, instead of equals, we can have one side of the line or the other side of the line, depending on less than or greater than, the inequality I've been talking about. And that's rather nice. In this case, we've got, if we want to maximise stuff, we want to look at materials above the line. Minimise, of course, could be anything below the line. But of course, it's always the case, we could always just go right to, in this one, if we want to say we want something with the highest possible density. Well, we go over here. If we want something with the highest possible Young's modulus, we just go up there. But we're looking at relationships here. One more thing. There is a summary of why the log system works. M to the e to the power half rho, rearrange a bit, it turns into a very nice linearised y equals ax plus b log equation, which is why it works in this kind of log-log chart. Now this chart, and about 20 of these things, are available on the LMS website for you to download as a PDF. If there's an exam question on this stuff, which there has been every year since I started this subject, in the appendix there are a series of these charts copied that you will be asked to engage with actively, just as you're being asked to engage with the charts for assignment DP1. And so therefore, learning then a demonstration of effective learning at the exam stage. So we've again got Young's modulus, density, nice and black and white, easier to print, at least for now. The shape, there's hopefully everyone who's watching, the essential shape is the same. Some in the room might be thinking, jeebus, it's very, very hard to see what's going on in that very densely populated zone, and that's why we have access to Cambridge Engineering Selector. One of the reasons is you can zoom in and you'll see even more material options pop up as you do that, which is part of the power of that software package. And again, I've just extra carefully highlighted those 3 lines. And by the way, those 3 lines are just guides for the slope. That's why in the exam there'll be rulers are allowed. The idea is you'd be able to get the slope of that line and put it wherever you like. And we've got here E on rho equals some, it should be M instead of C, but anyway, we've got all these parallels going up. Now, that's okay for that one, but what about the other 2? You'll be trying to create parallel lines if you have a certain kind of problem asking for that style of ratio that you just are looking for maximums. And again, it might be easy for you all to think, oh, well, for any of these things, we've got to, for any of these slopes will be up around here or here or here or here. And I'd say, yes. That's why I'm always going to make it a bit more interesting, as is reality. It might be, blah, 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 according to this a material index with some additional constraints. For example, must have a Young's modulus, no greater or no less than the least steel Young's modulus. I could do that. And in a minute you'll see the example. It must have a density such that it is lighter than water. And density of 1 is water, so that you're given another constraining line. So it's about regions of interest. And that's part of what a real engineering type problem can be, and the power of a chart of this type. And here it is. There's water. You could say, I want all the materials that can float on water. And I'm not talking about like a steel-hulled vessel where there's a lot of air gap inside. Literal block of material, put it in water and it'll float. Well, it's nice to see wood, cork, some polymer foams, but of course all the metals sink because they're higher density than water. Now, what's on the screen now relies, without me saying anything, it relies on everyone in the room appreciating that the density of water corresponds to 1 megagram per metre cubed. Now, that's another little hint about these charts. And it's one of the biggies, actually, that you have to be able to be confident and comfortable jumping between units. We're used to 1,000 kilograms per metre cubed. A megagram is, for me, was a bit of a conceptual leap. It took me a while to sort of get my head around. Okay, got to constrain myself to whatever these charts or Professor Ashby has provided us as units. That's a big hint for everyone in the room. Not so much for the assignment, because you've got lots of mentoring support in the design drop-in sessions to make sure you get it right. But in an exam, And if you don't ask the mentors and you just rush to Cambridge Engineering Selector at the last minute, you'll be working right at one end or another because your units are wrong. So pretty simple, but hint for now. Second thing to think about, and I'll go back a slide and get rid of all that stuff. These three lines, they're true and reasonable for the three different modes of use, functions, tie, beam, plate in a beam mode. But I can create, for learning and for the fourth lecture, there are some case studies. There's the potential to have any exponent we like, depending on the initial conditions. So, some years students are asked in an exam setting to actually construct the line on a log-log chart that corresponds to the input data. Remembering it's just a linearized form of an exponent, and once you've done it once, it becomes easy. But please make sure everyone in your team does it at least once, so that everyone in the team has a mastery for the exam. Here's another one. What about materials that are stiffer than steel? Now, it means that E greater than E of steel. So there's the limiting line. And by the by, we don't cut through the middle of the steel boundary. We have to, with that assertion up there, we have to think about the most stiff steel, because after all, it's a nice general concept steel. We can't, if you go for the least stiff steel, well, get a big cross and lose lots of marks. This is just, use of language. So that always, if I say something like that, always go to the upper edge of the boundary, as is up on the screen. So we've got our steels, and any material up there we can safely assert is stiffer than steel. A bit harder to see, and you've got to interpret on the chart. Really easy to see and interpret using the software. So thus, I've managed to, hustle the system of University of Melbourne so that we get the software for your use. And there's a little bit more on this chart just to make it a bit more interesting. Let's just say I have an exam and I can't be bothered giving you material properties, but I've given you all these, charts. I could have an example, I could have a problem with aluminium and you'll need stiffness. And I might even say the stiffest aluminium you can imagine. This chart will be in an appendix. You'll be able to read it off. Aluminium is in there. I'm telling you about it right now, so there's no excuses. And you can just read off, rough enough for what we need in a design setting, minimum and maximum values for aluminium. And 10, 20, 30, 40, 50, 60, 70. Well, it's in that 60 to 70 kind of zone. And, and that's all I'd ask for. I don't need high precision on rough, thick-lined stuff like this. The purpose is to demonstrate you can get the information from a resource, this chart. And aluminium's, by the way, Young's modulus, or stiffness modulus, is about 70 gigapascals, about a third of steel. So, hopefully that's in your head already. You can be confident with the number. Alrighty, compared to stiffness, now we've got strength. And you might notice a very different looking chart. For those people who have read ahead and already got the PDF of all the charts, those boundaries or bubbles, everything's different. And as it should be, because we're looking at different material property sets. Still, we've got density, as I say, looking at specific something like specific strength or specific stiffness. But for specific strength, we've got, again, these three guidelines associated with the three functions, straight axial tension, bending of a beam or bending of a plate. And I've just highlighted a few different boundaries, alloys or steels, metals, etc., polymers and ceramics. And there's, I think I've got this listed in a sec, so I won't talk about it yet. Just keep an eye on that dashy line around the ceramics. and if I haven't got it up on the slides, I'll be able to tell you. And also, don't forget to read the title block, because there's stuff in there as well. These are all, again, not meant to be super duper hard, just part of the professional engineer's toolbox, because it's easy to make a mistake if you don't take your time and go through the process. Now, in this case, we've got density of steel being a very thin variation across density, but a very wide variation from about 200 megapascals to about 2,000 megapascals. So mild steel, and you can imagine high strength, probably getting into brittle, spring-like materials. Yield strength is probably very close to ultimate tensile, all those kinds of things going on. But the point being, it's a pretty big range. You don't ever say steel, about 200 megapascals yield, because this little tool is telling you, nah, there's a whole family of steels. So you can go higher, but I can promise you, as you go higher, you go for that highest strength steel, then with CES, go and have a look how much it costs. I'll promise you, it'll be a lot more than bog ordinary mild steel down the bottom. By the by, there's aluminium. It's in that boundary there, and you can hopefully, even up the back, you can hopefully see that the density range is a bit bigger. Not forgetting that it's a log-log scale, so maybe it's part of the log effect. You can look that up for yourself. But again, aluminium can go all the way down to something very low and up to something very high. Now, as with anything, this is a snapshot in time. I wouldn't be surprised if the highest strength aluminium is of greater strength than 600 if you went to CES, the latest edition, and have a look at it now, which is something you could do for homework if you're interested. This is just material science, metallurgy, the whole world full of engineers and technocrats trying to push the envelope, optimise things. So don't just take that. That's why I put the approximately sign in front. It could easily be higher now, and that's something you could look at for yourselves. Now, tensile versus compressive. I thought I'd put it in. If and I've done this in exam settings as well, blah, blah, blah. It's a chain or a rope or a cable or some such. It's a tie, tensile, axial tensile loading, which means positive stress, which means that all the ceramics become invalid, because that dashy line and what's written in there, ceramics and glasses, compressive stress or strength only. So everyone in the room now will not make that, introductory mistake of saying, if I ask, give us the material that will cope best with this kind of loading as a cable, and you go up to diamond or silicon carbide or some such, boron or some such, you'll get a big cross, because you haven't read the chart properly, haven't looked at the title block properly, haven't attended this lecture, or you're half asleep right now. And these are the sorts of little things that I ask about. And you might think the bleeding obvious, but it's the reason I talk about it, because people do make the mistake. I can't presuppose that everyone has got it in their head that this is how you go about the to be blunt, day-to-day process of being an engineering designer. It's not all about creativity. Some of it is just about looking at the resources and looking at it correctly. Now, I didn't mention the idea of cost. Right now, you never go out to material suppliers and say, hi, I'm a University of Melbourne person just for my academic study. Tell me the cost of such and such and such and such. Please don't do that. We get angry emails and phone calls. But when you're a capstone project student and you're working with an industry, you can say, hi, I'm working with industry X and I want that cost value. Perfectly acceptable. Because the company will then think, I might get a contract out of this, or a payment for stuff. Right here, right now, all I need from you is to recognise money, that it costs, we don't have unlimited funds by and large. And for people who did mechanical design with me last year, you might remember the one counter-example I have to that is the McLaren F1 road car, and it had gold plate inside surface of the engine bay to reflect the engine heat away from the carbon fibre frame. And the chief engineer spoke to camera saying, "It's, you know, money was no object for this design, for this production car, so, and 24 karat gold just happened to be the best reflective material." That's the one example I have where we didn't have to worry about cost. Everyone else has to. And so as far as we're concerned, I may ask questions, and I have in the past in exams, about blah, 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 material selection, give us your best candidate material, and then I might say, how does that best, your preferred candidate material stack up against other candidate materials that will cost, blah, 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 have a relative cost per unit volume. And all I'm really asking you to do is use this chart. And I'm just highlighting a few things: copper, nickel, titanium, and a little comment. The most expensive copper alloy is cheaper than all the nickel and all the titanium alloys. That's one of the things that this chart is telling us. So there's copper, and by the by, I presuppose that the class, sometimes I put the symbols in, but I presuppose people understand what the periodic table is of elements, and that the symbols therein, where they've got, carbon fibre reinforced polymer, titanium alloys, nickel alloys, copper alloys, and you notice this one doesn't have PB for lead, as lead in full. That's just part of the learning I would hope that you would achieve. Sometimes I don't put, what CU is, because I just expect, that copper is something that everyone would be appreciative of. So the most expensive copper is cheaper than a lot of other stuff within that envelope. So just something, and they are rule of thumb insights that this stuff can provide you with. Now, of course, I keep having to say this: don't go into a job or even a vacation job using this chart to help make decisions for your client or your company. This thing is only as accurate as the last time that other engineers back at Granta Design, who produced CES, looked it up, wrote it into their spreadsheet so that this table could be produced, or this chart could be produced. But it's good enough for learning, for the here and now. Now, to an example. Materials for oars, rowing oars. Same kind of layout as before. Function, objectives, constraints, free variables. Well, the function is an oar. We want it light and stiff, and it's a beam. It's got to have minimum weight. It's got to have a certain stiffness, and it's also got to have a reasonable cost, and it's got to have an adequate toughness. And we're looking for a cross-sectional area material that we can then select. Now, this box here is an oars are stiffness limited. That is, how much flex or how much, cantilever spring effect does the oar provide the rower? And now, I'm not an expert on rowing, but I do know there's an expectation that as the paddle goes into the water and the rower starts pushing on that you're not going to get infinite stiffness. You don't want that. You want the rower to do what it does. The oar flexes a little bit, and as the density of the water, the resistance to motion of the water kicks in, you create like a bow and arrow bow effect. Rower does his or her thing, and then the last little flick from that oar in the water keeps the boat moving, out goes the oar, and you repeat. So there is a certain amount of deflection sought. You don't want it infinitely stiff, but this is, there's some kind of happy point that only those who focus on this stuff deeply would know about. And they're loaded, oops, sorry, wrong button. And I buggered up my reveal. And they're loaded in bending. Now, this is an example of what I call structural distillation that was taught in third year, and I expect everyone in the room to be aware of. The one thing that stops this from being a total free body diagram is a reaction force at the pivot point at the edge of the boat. Simple stuff, really, but there's an expectation that everyone has an expectation that an engineer should be able to do that. So, don't forget the maximise versus minimise, and I've got my material index M there. Density, Young's modulus, the equation is as per what I introduced before. We've also got a fracture toughness value there, which will just sit for a second. I haven't taught you about fracture toughness. I did tell you what it's about last time, and you might notice the units. Megapascal, metre to the power of a half. It ain't megapascals. It's something else. But again, Young's modulus versus density. We've got the material index equals e to the power of a half on density curve or straight line. And we don't just leave it down here. Where is it? There. This is where having a rule is good. You just parallel to that guideline, move it up and up and up and up. And we get this sense of, okay, we've got some woods, we've got some carbon fibre, we've got some ceramics, but not forgetting that ceramics aren't very good in bending, so we might not worry about that too much. And so what else is there? Wood, carbon fibre, beryllium of all things. That's up there, the B. And a few ceramics, fracture toughness will be inadequate, tensile strength will be inadequate, a few things there. Now, one thing is that ores, because ores exist, we know what they tend to be made out of. Either wood, or there is a bit of carbon fibre, also carbon-filled reinforced polymer, and there also are a few hollow aluminium ones around. That's just FYI for those who've never rowed before. But for now, we worry about this, which is that, I talked about, minimise, maximise, less than or equal to, greater than equal to type stuff. Well, the red line here is the equal to, and the search zone is above the line. Because, we're looking to maximise the efficiency. Because if we weren't, we'd just be going, we could be, keep looking down here at this stuff. Lead. Will we make it out of lead? Or will we make it out of some kind of elastomer or plasticised PVC? No. Hopefully everyone in the room could think, no, that's we get the intuitive, incorrect answer, which means we must have made a mistake somewhere. So, above is where we're looking for. So, now, this is where CES comes in. I've now got a CES snapshot of a zoomed region of the same stuff. And so you can see some of the various materials and where they sit relative to a limiting line. And that's something, the student who wants 10 out of 10 for some of those more explorative type problems in Design Project 1, this is the sort of stuff that you'll do within your team. Same deal yet again, and even more materials are shown, the same thing, just represented in a different way. And a lot of words which I'm not planning to go through in great detail, except to say we're looking at solid circular section, which is a very interesting point. Wood, it's pretty easy to make. A dowel of wood, which is solid circular section, and have our ore made out of that. Carbon fibre type stuff, or carbon-filled polymer. Is that filled or is that hollow? Well, how do we compare? Is it apples with apples? Or are we comparing two different things? Well, the answer is, as all that stuff up on the screen, we are comparing two different things. We do have to think about this area if we're going to be, true to what a design of an ore is going to be. So, and that's in red down the bottom. Here's a bit more stuff, though, just for now. And I'm not going to read all this out. I did raise the idea of toughness and fracture toughness at the outset. Now, even, if someone says toughness is important, and you say, oh, okay, toughness corresponds to this and this and this, okay. CES, as a product, and I think I've got a toughness chart in that PDF for you guys as well. You can actually get a chart that has various toughnesses for various materials and have a look. The limiting line, the limiting point is going to be difficult to know because after all, if you haven't got a feel for what toughness is and what range of toughness is, that's problematic, which means back to resources, back to experts of some form or other to get a number for this GC notion. And GC corresponds to fracture toughness divided by Young's modulus, by the way. So then we could think about, well, okay, we've got a toughness value. This one is just for the sake of, in CES it's great because you can get rid of all the clutter. You can just have your candidate materials from a first pass of what I was doing with density and stiffness, and they go into this chart of toughness versus cost. Now, what's different about this one is that we've got two rectilinear lines, a horizontal and a vertical, that provide us with an area of interest. And that helps us narrow down our candidate materials. Now, this is where the software is powerful because it allows us to grab the subset of candidates and put them into the next set of constraints, what's up on the screen now. The charts, just by themselves, don't let you do that. And so you're a little bit limited. But I'm telling you about this in sort of a long-handed way, just so you've got in your mind that flow chart of process. What's the most important, then what's the next most important, and how can we make it systematic in some way or other? And up on the screen, it's easy when you've got some software to give you a hand. Now, the but. This outcome is limited in scope because it's just presupposing everything's solid, and it's not. Ores are often hollow, as I've said. They can even have varying geometry along their length, and aluminium is good for that. So how do we accommodate I-beams, hollows, tapereds, triangulated, etc., etc.? Well, lecture 2, which I'm about to start, talks about that. So don't go anywhere. I'll just pull up the next slide set. To go. Maybe you've been very polite. I might do something else instead of starting with the slides. How far in is it? Oh no, that's okay. We'll start on this. People who were here earlier would have seen I had a video that I was playing around with to see if it worked. I won't show it now. I'll just get through some of the what I regard as the more boring but still important for you stuff. And video at the next lecture this week. Okay, shape. Lecture 2, efficiencies, shape factor, a new thing, phi is going to come up, and then the modified selection procedure. Okay, so shape factor will allow for the issue that I raised with the ore. So now instead of just having function, material and process, we've also got shape to have to deal with. And again, we've got the tie, we've got a beam, we've got a shaft this time, and we've also got a column. And for anyone who's forgotten, axial tensile, bending, sigma equals my on I, tor equals tr on j for twisting, and again, for compression, it can just be as simple as F on A, or we have to go into Euler-type Johnson calculations for columns, whether they're long or short. And that's just, I actually covered that in one of my lectures on structural integrity. So we need to think about what is the best combination of material and shape for the load that we've got being applied. Now, this little slide is just a starting point for this, and the key word, I should perhaps have it even bold, dimensionless. Now, shape factor has got nothing to do with the size. It is the form, and that's what this is trying to get at. The material plus a micro shape gives us this idea of a shaped material. Now, if we had, and this is where it's an ambiguous thing, Ashby mucked me around and you around on this. Let's just go with solid circle, so a dowel, as I said before, solid circular section, phi equals 1. And phi equals 1 independent of how big it is. In a little while, I'll show you some evidence where Ashby turned it into phi equals 1 for a solid square section. And the circle is like 1.05 or something. But we'll get to that. But what this slide is trying to show is that the amount of material, if you like, or the area, the millimetres squared area of that solid circle corresponds to the millimetres squared area of material of that circle and the millimetres squared area of that I-beam. Same for the second one here, more material, bigger circle, more material in the hollow circle, more material in the I-beam, and to the third one, same deal. So you just got to consider that I could have also had A for area equals constant for each of those sets of 3, or columns, if you like. What's also nice about where we're going to with this is that if we have an I-beam, and I'll talk about this BE in a second, this is about bending. We have about 10 times stiffer in bending than a solid circular or square section of the same cross section. And circular tubes are in the same kind of ballpark. And that's, you've done all this in an earlier subject. Second moment of area is sort of one of the big things we're going for here. And so the same amount of area, change the shape, and we get advantage, engineering advantage. And you might think, fine, but this phi gets its power in that it can be incorporated into the equations, into the charts, and then we can have a look at all of commercial available shapes as well as other material properties. And there we are now. E corresponds to the stiffness constraint, and B corresponds to the bending function. So FYI. So shame I didn't have it all the same scale, but anywho, that's what the sub and superscript are corresponding to. Now, this is where this slide is trying to indicate the limitations of some materials and how they can be formed. Now, timber, the ore, solid circular section, pretty hard to put a hole through the middle of a piece of timber when it's as long as an ore. Easier to do it with aluminium and even carbon fibre. Timber, hopefully everyone in the room can sort of appreciate that until we start laminating timber, it has to be pretty proportional. Now, we can't have it too thin or it loses its material, any kind of material property. It'll just crack and pop due to the grain structure of it. Now, I'm not saying it limits or saturates at 2, the ratio base to height of about 2, but it's not going to be as high as 10, just as a tree trunk cut up. Whereas an I-beam, can go to 10. It can go higher. How much, we may ask? Well, we'll get to that in a minute. And CES can help, but we'll be getting it in this lecture anyway. So just because you might say, I would like to have a shape factor of 10 or 1,000, doesn't mean that you can actually get a material that can achieve that for you. So that's just another little learning thing for today. You've got to limit your scope or your imagination to what is achievable or what is available. So, I'm sorry, lots of words, but you don't have to read them. I am not going to read them all now, but I'm just going to first point out we've got this square section now. This is, again, just to try and muck you around. We've got B times B, A equals B squared. It's up there, it is up there. And we're looking at other functions. We're looking at this shape factor for elastic bending, and we've got the stiffness via stiffness naught for the square, I versus I naught, same E, and we're getting to another function, one of these nice little functions, nice and general. So sigma BE is going to be 12 times I on A squared. So that's a starting point. When we go right back to these stiff lightweight beam, as per, I think, one of the last things I talked about last lecture, we want to incorporate phi. Now it's easy, and hopefully everyone can see it's just in there. We've got a new area incorporated into our material index equation, get rid of all the constants, and now we've got phi to the power of a half. So, and this is, again, the learning for today, phi is inside the bracket. So phi is to a power of a half, E is to a power of a half compared to density. It's not just a linearized adjustment when we start engaging with the material selection process, which is a rather nice thing. And the logic, all the logic you need in full is on the screen now. For strength, similar process. We get down to a phi where I've got Z equals I on Y max. Hopefully everyone's aware of that. Second moment of area, distance on Y max is the distance from the neutral fibre to the extreme, a neutral axis to the extreme fibre. Sorry. And we've got another pretty simple equation to deal with. Now, for a strong lightweight beam, same function, objective constraint, and I won't read all that stuff out, you can do that in your own time. We get to choosing materials now with the smallest density. We've got our stress function, and by the way, F is a failure. F for failure. It could be ultimate tensile, it could be yield, it could be proof, depending on the material. We're used to steels, but not every material fails in the same way. And that's why Ashby chose to put sigma F. And we've got the sigma again inside the brackets of the power associated with our exponent. So, by that same bit of logic, for torsion, bar or tube, and that means continuous around the outside edge. I don't know at what stage you study torsion on a discontinuous object, but all I'm worried about here and now is continuous. When it gets to discontinuous, all bets are off and it gets really, really hard. So we've got our equations and our associated shape factors. Now, if I have an exam question on this stuff, I do not expect memorising. I will actually provide, stiffness limited, and I would probably just cut and paste this sort of stuff in. What wouldn't I give? I'd probably give you the table for K, but not that sentence. I'd expect you to know that you've got to look up K from another resource, which I'll talk about in a sec. So it's a resource. It's something that you use. Ditto with columns. Stiffness and strength limited design. Choose materials with the smallest values you see up on the screen. And what's nice is that when we look at ties, that is axial tension, and I've got this big strike through that, there is no shape influence on ties, which I'd hope everyone would think, yeah, that makes sense. Other than edge effects, stress equals force on area, why should the shape of the object really have a big impact? It probably does have some impact, but not anywhere near as much as columns or torsion or beams. Thus, bunk, bunk, bunk. We, at this stage, can just say, don't worry, it is invariant. And again, that's the sort of thing that in an exam setting I could play around with. Now, I did promise I'd get to these factors, and here they are. I'm going to go forward a slide quickly. Stiffness, bending and torsion, strength, bending and torsion, and, oops, have I gone in the right? Yeah, right way. And we've got all that summarised in those nice little phi, super and subscripts. And I'm not expecting you to be able to read all this stuff up the back of the room, but just to know that the resource exists and that you think, that factor, yeah, it's there, get it, use it, acknowledge your source, and we're done. I'm going to zoom in now, boom, this one. Now, that blue box, circles versus squares, and I did indicate that variation. Well, in this edition of Ashby, solid circle, 1. Solid square, same area, 1.05. So it's a 5% difference, which isn't much, which makes me understand why Ashby didn't worry about it so much. When I'm talking about tens, and I can promise you, it gets up to 60s and hundreds in terms of this shape factor. So, 100 times versus, times, 1.05 is not a great variation. So that's part of the reason. When it gets into more sophisticated shapes, the equations themselves get a lot more sophisticated. One thing, my job in an exam setting is not to make you hunt around for big fancy equations and put lots of numbers in and then make mistakes with the algebra. That's not my intent. So don't ever sort of overstudy this stuff. If I'm going to ask a question of this type, this table will be in the exam and your job will be to find the correct equation for phi and make use of it. Now, here's the 4th edition of the same book by Ashby, and at this stage we've got square equals 1 and the solid circle equals 0.955. So I've met him, but not since I found this out. So I'd love to ask, why did you change your mind on this, Michael? But I don't have an answer. And so I've shown you this in part because I know the guy and I'm a bit confused myself. That's why I scratched my head. But this is just in our world of engineering design, what I'm just showing you. These are published books. Michael Ashby is a world-renowned engineering academic. And I don't know why, but it's there, and it's an ambiguity. This is something that engineering people have to deal with. We're not dealing with truth like maths. There are these sort of percentage variations. And if you're aware of it, that's okay. Identify it. And that's all you need to worry about. Hopefully everyone can see that this is a later edition. It's a bit fancier. And again, there's the table. And I think, this is for K. I did say I'd mention it, and there it is. When we have twisting, torsion, different set of equations, and just like everything else, you've got to make sure you read the title or the caption or the footnote, whatever, to make sure that you're getting the right equation or number for the right application. I think it's now time to go. So I'll see you next time.
Tomorrow's design rubber session also about CES. Tomorrow's design rubber session also about CES.
Well, I've written all that down on the website.
Okay.
And it's all explicitly stated there, so I can't tell you exactly, but I can promise you it's not in room B102. We don't have it booked. It's in room 207. You can ask questions about CES, but you're not going to get much of an answer because they're not in the room to talk about the computer package.
I have some questions about the slices. So from here,
Well, that's a deep. I know I answered the last guy, but I'll just